All right, so we're ready for lesson 10, example 9. So what is the change in gravitational potential energy of a 1200 kilogram satellite when it is launched from the surface of the Earth into a geosynchronous orbit? So what we're looking at here is examining the gravitational potential equation as it relates to the much larger version. So we're looking at UG is equal to negative big G M1, M2 over R. So this is a little bit different than our gravitational force equation since it's R rather than R squared. But this is the equation that you did see in the PowerPoint for gravitational potential energy. So we're looking at the fact that we're changing this from being on the surface of the Earth, which is our initial radius, to being in a geosynchronous orbit. We can go through the whole long process of finding out what is the radius, the orbital radius of a geosynchronous satellite again, or we can look back into our notes and see the fact that our, using Kepler's third law, we are able to see that when a satellite is in a geosynchronous orbit, it has an orbital radius of this. So we are now going to look at our change in potential energy. So remember, our change in gravitational potential energy is going to equal my final minus my initial. In both cases, the masses of my two objects are remaining the same, M1 and M2, the mass of the Earth and the mass of the satellite, and the gravitational constant is going to remain the same because it's a constant. What is not going to remain the same is this R term. So I can simplify the way my math is being written by looking at that same equation like this. This does mean the same thing as taking the final of G M1 M2 over RF minus my initial G M1 M2 over RI. I just factored it into something a little bit neater. So now we can go ahead and plug all of our numbers in. We have the mass of the Earth, we have the mass of the satellite, we have the period. This period was actually used to find my orbital radius, and we have our two radiuses, or radii. As a result, we do see when we plug everything into the calculator, we get a change in potential energy of 11,471 joules. If we go ahead and round that to sig figs or put it in scientific notation, we get 1.15 times 10 to the 4th joules. So this is our change in potential energy for our satellite when we launch it into a geosynchronous orbit. So now we want to go ahead and take that one step further. We want to look at what is the total change in mechanical energy. Well, our change in mechanical energy is going to equal our final energy minus our initial energy. We could also look at it in a slightly different way. It's going to be the same thing as saying our change in mechanical energy is going to equal our change in kinetic plus our change in, potential. Well, we already have our change in potential. We solved it in part A. So now we need to go ahead and find our change in kinetic. So kinetic energy, as you recall, is equal to 1/2 mv squared. So we need to know what is the speed of our satellite as it is orbiting or moving in different parts of the Earth. So our initial velocity for this is going to be what is the speed of that satellite as it sits on the surface of the equator orbiting that particular point. So we know that velocity is equal to distance divided by time. Our distance is the 2 pi r initial, and our time is that period. So we have that 2 pi times our r initial of 6.38 times 10 to the 6 meters, and we have our period of 8.64 times 10 to the 4th seconds. As a result, we do get an initial velocity of 464 meters per second. So that's the velocity of that satellite as it sits on the equator moving with the surface of the Earth as it rotates. So now we're going to look at what is that velocity now that it is farther away from the center of the Earth. Well, it is now our final radius that we're looking at. All right, but it's having to cover a much larger distance orbiting the Earth, but it's going to do so in the same amount of time. So we are going to see the speed go up significantly. So we're going to see a speed of 3,069 meters per second. So we have our initial speed of our satellite moving on the equator. We have our final speed of our satellite now in a geosynchronous orbit about the Earth. So we can look at our change in kinetic energy. All right, our change in kinetic energy, we're not changing the mass of our satellite. So when we write this, we can do some simplification, and we're able to say that this is our change in kinetic energy. We're going to plug in for our final velocity this number, and our initial velocity is going to be this number. When we go ahead and figure that all out, we get 5.52 times 10 to the 9th joules. All right, so our change in mechanical energy is going to equal our change in kinetic plus our change in potential. So we have that 5.52 times 10 to the 9th joules plus, from our previous problem, 1.15 times 10 to the 4th joules. When we add these numbers together and adjust for sig figs, we actually see the fact that our change in mechanical energy is mostly due to our change in kinetic energy. That change in height is very, very little, very, very small compared to that change in speed that we saw here. So most of our change in mechanical energy does come from increasing that speed to get that satellite to orbit at some distance away from the Earth. There is one little last question attached to this, and that is, why do you want to launch satellites from locations that are near the Earth's equator? Well, we want to get as large of an initial radius as possible, because the larger the initial radius, the faster that satellite is initially moving. If we were to launch from something closer to the North Pole, that radius, the initial radius, is a lot smaller. As a result, it's not going to be moving as fast. So we're going to have to apply an even larger rocket to our satellite in order to get it to orbit the Earth.